Hey, what's up, everybody? Just chilling out. Got some office hours going. I see we got a few people watching. Who all is here? Who all is here? Is it 0 people? Maybe we have 0 people watching. You never know. Let me look over here. No, it's just 5 people. We got 1 like. Thank you for that 1 like. Maybe I just liked it and got that 2nd like. So thank you. Oh, 3 likes. Hey. If you're in the chat, say, hey, is Mubot awake right now? Hey, yo, good to see you here, Michaela. Let me go over here, look at the console. Good to know. Oh, wait, we got to reset. Mubot's got to wake up. If you have questions, let me know what you're working on. I got the coffee. Ivan's always lurking here. So good to see you. Thank you so much for the liking the haircut. My fiance cut my hair, and I said thank you. She did an excellent job. Brian, can we discuss 3A, B, and D? I have things for A and B. Get confused? Yeah, I'm doing well. Doing well. I got my coffee. So just I don't know. I've been on this whole like workout health food thing. I've been eating way more fruits, way more vegetables. I mean, who'd have thought those things help you feel good? I've been told that my whole life, and I was like, I reject that hypothesis. I'm going with the null that we should eat cookies, candy, and drink coffee. I've kept my coffee, but I've dropped the cookies and candy and ice cream, all that good stuff, and pizza and burgers. I mean, I'm getting old. I'm getting old, man. On a more serious note, I think it's important to have a balanced diet. I've always thought that my whole life, but I think many of us, I'm pulling up the assignment right here as we speak, many of us strive to have a balanced diet and then just fail at it because it's so hard. It's hard to buy fresh fruits and vegetables. It's like you want to buy that stuff and then it's easier to buy a box of Swiss cake rolls. So, that's what I do. Man, Swiss cake rolls, don't buy me a box of Swiss cake rolls. That is the best, worst thing in the world is Swiss cake rolls. Because, man, you eat one and you're like, oh, it's so good. And you see another, like, oh, man. Here we go. Let's take a look. I just miss Swiss cake rolls. That's what I miss. We got the assignments up. Let's do this number 5. You bet. Number 3 and number 5. I think we got number 3 right here. Let's go talk about this. Let's hop to the main screen. So here is question 3. I'm going to zoom in on it a bit. I was getting it up as we were talking about some Swiss cake rolls right there. So correct me if I'm wrong. This is the one you wanted to talk about here, I trace. Is this correct? What about these plots might suggest an association? So I'm going to take a screenshot of this and kind of zoom in on it. There's our correlation stuff from today. And when we're talking about associations right here, what does association mean? Well, an association is when knowing like what day of the week it is might tell you something about demand. Does that make sense? Like an association is when knowing X gives you information about Y. Now, would these be correlated? Because I can see right here on Thursday and Saturday it looks to be higher, and on Monday and Sunday it looks to be lower. So could these be correlated? Kind of a test question right there. Could these be correlated? Could day of the week be correlated with demand? Trick question. Something we kind of reiterate a lot as stats people. Could day of the week be correlated with demand? Could day of the week be correlated with demand? Actually, I think that's wrong there. Be careful. They could be associated, but not correlated. So unless you're saying as the day, you might be a way to twist it to be like later days of the week. Like as day of the week goes to a later date, demand gets lower. So we do see some sort of you could maybe do that. Maybe there's a way. But correlation is always going to be between when both variables are numeric. And so what we're looking at right here are side-by-side box plots, which implies one of the variable. And this is kind of a nuanced thing. Like a lot of people will just say a correlation in general. But this is a correlation is a specific type of association. So since the X variable here is categorical and the Y variable is quantitative, we're going to say that they're associated. And what does that mean? And I think you're getting it right there, Trace. There's fluctuations in the medians, which we see right here. So we see some fluctuations in medians. And it's not just that. So there might be a way, I agree right there. There might be a way to kind of say like as day of the week goes on, we might see some sort of positive correlation, like as it goes to a later date of the week, as a higher day of the week. Which we don't necessarily see that, but there might be a way to twist it. The way we're viewing it visually right here, we wouldn't talk about correlation, we would talk about association, which correlation is a specific type of association. Does that make more sense right here, Trace, on the first part? Yeah, we got to remember too that this is in units of 2000. So this difference right here, which this might answer another question, this difference right here might be about 600 maybe, because this is a difference of 1,000 because I'm breaking this scale apart. So maybe that's a couple hundred right there, which if we're selling a couple hundred more bikes as a median, that'd be higher. It's, we need to look at the p-value. We need to ask our bosses if they care. Like if our bosses only care, hint, hint, hint for later questions. If our bosses only care that there's differences among 1,000 between the days, then we don't see a difference of at least 1,000 between the days. We see a difference of 600 maybe. Monday and Saturday look to have one of the biggest differences between medians, and it's nowhere near a difference of about 500. I way overdid this on the drawing down there. That is visually what a difference of about 500 would look like, and our difference between here is probably closer. 1,000. Excuse me. That's a difference of 1,000, and our difference looks to be a lot smaller than the difference of 1,000 because this is 4,000, 5,000, 6,000. Does that make sense there, Trace? That this difference we're observing right here is not in the realm of a difference of what 1,000 would look like. It's a couple hundred, 500, 600 maybe, something like that. I think I can actually numerically find the difference with some code. Let me find the numeric difference. I think I know what data set this comes from. I think it's EX6 bikes. Let me double check. And we can use the aggregate function. Does this have weekday? Does it have day? Yeah, it has day. Okay, good. So we need to use the function. This is not required. We need to use aggregate. Aggregate can use the formula function, I believe. We want to aggregate demand by day. And we want to use fun equals. No, we got to do data equals EX5 bike, and fun equals median. X is missing with no defaults. What is the aggregate I'm mad about right there? What does that not take? There we go. There we go. It doesn't. Sometimes the functions take the parentheses inside of it. Sometimes they don't. And you can see right here, we could sort this now. Let's just go here to store this as X. And let's go to sort. I think sort X should work on it. I didn't capitalize my X. And let's go to order X. There's the, what's going on? Brain, what are you doing? X is a data frame, right? So if X is a data frame, look at me not coding well today. Oh my gosh. What? Really? Okay, good. What did I do? Oh, I appended code. So let's go here to X, order on this, and do this. And there we go. That's got it. Cool. So Monday is the lowest and Friday is the highest. And we could do like the max minus the min, but we can see here the range between them is not even 400. So this is actually the actual answer right here, which you're not required to get. I was saying it was probably about 500, 600. And the biggest difference is between Monday and Saturday. And so Monday being right here and Saturday being right here, this is a difference of about less than 400, I think. We can numerically find this difference. Just take this minus this. It's going to be negative, but that's okay. 333. So that is a difference of 333. So definitely not what our managers are looking for. Much smaller than 1,000 difference, just visually speaking. And this is the biggest difference. Luckily, they're next to each other. But if we have the data, it doesn't tell you which data set this is because we do want to be able to visually inspect stuff. But if we have the data, we can look at this. And this code up here, the aggregate function, which is such a cool function because you could just change this right here and get the means for each day. And so just instantaneously, and we're saving it to X right now, the data from X. But now you can get the means for each day. You could do standard deviation. All this stuff right here is such a cool function. Like the aggregate, you can even aggregate by other things like holiday. So now we can get different groups right here, and there's not enough data for those to get those data sets. But aggregate's such a neat function. So, and we haven't even used that one. There's just so many functions. You got to keep them all in your brain up here somehow. At least try to memorize the formulas. So Trace asked more here in a moment. We're going to hop to the screen and we'll take Aisha's question next. Let's do this. Okay, Aisha says, for 5A and 5B, do we have to show two different data sets, one with 500 permutations, one? Yep. It'll create a good bit of output. Do you want me to go over that here a little bit, Aisha? Was that the one that Michaela was asking about? Michaela was saying going over 5. So let's bring up 5 right here, and then let's talk about it. And you're always free to ask questions. You have questions that go above and beyond. And thank you so much. We're throwing some 20 points. If I ever say not quite or close, just realize we're all here to learn. And I appreciate it because we're all just like, we're making our knowledge exact. That's what we're here to do. So let me get number 5 up and going. Where'd the book go? Number 5. Let me double check and then the activity or the assignment what it is. Number 5 is exercise 6. Exercise 6. And this is the tips data frame. Okay, cool. Exercise 6. Here we are. Let's hop over to it. Let's go to the main screen. I've been meaning to make an extra button right here. So using the ex2.tips, the data set records records the bill and tip amounts along with the tip percentage, as well as the party size, who was at the table where they smoked, and what time they visited. We are curious whether there is an association between the party size and whether they smoke. Party size ranges between 1 to 6, so in this case it is appropriate to compare the averages. So we're going to compare the averages when y only takes on a few different values, because there's not going to be extreme skew right here. Like there's not going to be an extreme outlier with 1 to 6. So we're just saying, okay, there's no extreme outliers. So even if it doesn't look perfectly normal. So regardless of what the distributions look like, we're going to use means right here. Run the associate function to perform a test of significance using the default number of permutations. Why is the test inconclusive? Now, one thing I want to point out right here, first off, in your code, you'll enter in your student ID. So I'm just going to enter in 123. That's not your student ID, and that's not anyone's student ID. That's just a random number. But entering your student ID right there. When we go to library reg class right here, it's going to load reg class. Make sure anytime you're working with a reg class function or data set, you have library reg class loaded, and that brings up all of the cool reg class stuff, which is right behind my head right there. Reg class is a package that contains functions, contains data sets. So you're just getting all these neat little things right here inside of here, different packages, different functions that we're using, such as like the associate function or the extips data frame. To confirm that ex2.tips is in reg class, you can see right there, it's basically example 2 tips data frame. And so it's just a exercise data frame for us to use. It can be in quotes or not in quotes, and that loads it into the global environment. And it's kind of just sitting here in the background, and you grab it and you say, hey, I'm loading you up. And it says, I'm here now. This is going to set the seed, which sets the randomness to your student ID. That way, anything you do is replicatable from here on out. And this is going to then create your random sample and write it over this right here. Now, you'll notice right here, let me just show the code again. When we load up ex2 tips, this right here is going to take, let me double check something. Okay, that worked. Didn't break it, luckily. Oh, it's taking less. Just making sure I can't break it. Okay, sure. It's working. Please tell me something breaks. If it breaks, just be like, yeah, Brian, this broke. And I'll be like, oh, no. Okay. So this right here, we've got our random sample. And now let's go ahead and start thinking about the associate function. So that just takes a random sample on line 114. Under the associate function, we are going to enter in the formula format, which is y tilde x. And then we're going to do comma data equals. So we have here y tilde x, comma data equals, just making it nice and big so everyone can see. Y tilde x, comma data equals. We'll put in the data frame name. And we're not going to change the permutations yet, but we do have additional arguments to change the permutations if we want, which is how many random samples we are taking to see what would occur by random chance. And we are analyzing in this one. Why not? I'll do it a little bit here. And we are analyzing. Where'd my thing go? Really? I closed it out that quickly. Now it's back. We are analyzing. I don't want to do the wrong thing. Party size between smokers. Okay. So with party size between smokers, we are going to go and we are going to go to I'm going to do a trick. The trick is attach. Gotta be careful where you decode. Code can easily make mistakes. Put it up here if you're going to resource it down here. And we have the tips data frame. We need party size. Oh, it's size of party. If you scroll down here, you can see where it says size of party. So really, go away. Size of party right behind my head. Boom. Size of party. And we're analyzing if there's a smoker. We'll decrease font size because we're going to need that. And ex2 tips is the data frame. It's made about my graphics. Be careful. If you have this very small, it won't want to make it. And now it'll do it. So we are getting the output. So you can get a graphics error right there, or it just won't let you make the graphical plots. And let's see if we get, we actually get a conclusive result. Now with this right here, I'm going to change the seed inside of here. This is an error that can occur. Or it's just so I didn't have this occur yesterday or 2 days ago when we did it. Now we get like the perfect inconclusive result. Now I need people to respond in the chat. Why, and this is not the interval we're using, why is this interval conclusive? And let's look at the notes. Someone just explain for a moment, why is this interval conclusive? That's not the one we're using. We're using means because we decided upon it, even though the data's got a weird structure to it. The QQ plots don't look perfectly normal, but it's due to it being very integer data. And there's not extreme skew. There's problems here on the high side, but it's very strong integer data. Why is this interval conclusive? Very important thing for the test. Why is this interval right here conclusive when it comes to determining the p-value? Exactly. Which we're not using that one. And so we're using the medians right here because you could use medians, but for this example, it kind of directs us in a direction which some people might say, well, since there's not a lot of values it can take on, and so I think you're pointing out rightfully so. If it does have skew, that's good evidence to use medians. This one's not so bad. And what you'll notice right here, this issue is due to the high amount of integer values where we see 2, 2, 2, 2, 2, 2, 2, 2, 2. That's the observed values right there of 2, 2, 2, 2, 2, 2, 2, 2, 2, 3, 3, 3, 4. And you see the values right here and what we would expect given normal. And this question does direct us to use means. It's kind of like, should we? I don't know. Statisticians will argue about this one for the end of days. They'll be like, no, use means, use medians. You could lean either way because there is theoretical reasons to use the mean and there's theoretical reasons to use the median. Due to the lack of extreme outliers, we could go with means. And a lot of people like to go with means, but due to the skew, we could go with medians. But the question itself, the way it's written in the book, we're just going to say, well, the book tells us to do this, and then we can blame the book. Increase your graphic size window. Increase the graphic size window. If it's a little tiny window, make it bigger, and that should fix it. Tell me if that fixes the issue, Michaela, right there. The p-value of the ANOVA doesn't mean... Yeah, change the seed really quick. Try that. So if you're running into issues where you are getting a conclusive result, go over here to the seed and change it, and then you should eventually... It's likely you'll get one that is inconclusive, but I think maybe there's a 1 in 8 chance. I could actually like run a test. You know what I might do? I might do that here at the end of this one. At the very end of this one, I might run a test, because if I can extract that information, I could run a test to see what % of the time you get an inconclusive interval by like random chance for this question. I like this question a lot, but it's just hard to like, because since it's due to randomness, you could get a conclusive interval. We saw that originally, but that's inconclusive. And then here's our original result, which was a conclusive interval. So this is conclusive because it's completely below 0.05. We were talking about this in the notes today. Those are, let me unfull screen this. Good. We went over this yesterday and today when we were talking about right here, whether 0.05 is in the range. So you can see right here, this interval is inconclusive. This interval is inconclusive. Let's highlight them. This is the only conclusive interval, and the other intervals are inconclusive. So this interval right here is inconclusive because 0.05 is in the range, and this interval here is inconclusive because 0.05 is in the range. The only conclusive interval is an interval that does not have 0.05 in the range. The question asks you use the default permutation. Yep, 500. Yep. So you don't need to change that. Good question right there. You don't need to change the permutations. This should give the exact same result right here as we saw. That's not the current results, but by default, permutations will do 500. You can also see this if you look at the association function. And you can see right there, the default permutations. So it's already putting that argument in there for you. If you don't put it in there, it'll set that argument to that without you entering anything in. And so the seed, well, the seed controls the randomness. So I will get the same result as I just previously got. If you notice, this is 0.021 to 0.056, and we get right here 0.021 to 0.056. So this is the same result whether or not I include the permutation argument. I did not include it here. Or if I include the permutation argument, I included it here. It's the same result. I was thinking the seed and permutation. Yeah, no, great questions, Trace, 20 points. Keep asking those questions. The seed controls the randomness. The permutation controls how many random chance permutations we do. Which you can see down here, we have 1 permutation now, which goes super quick. Now we have 5 permutations, which controls how many kind of random chance permutations. And then the way in which they're created is controlled by the seed. This doesn't control how many there are down here. It just controls the randomness that creates them. So it is connected to the permutations, but it's not how many permutations. It's like a Minecraft world. We always talk about like Minecraft. It just builds that Minecraft world for you, so that way you can go back and be like, oh, 0.716, 0.716, and you'll always get that same result. Every time you run this, your result is going to be identical unless you turn off the seed. And if you remove the seed, now you're just going to generate randomness every time. Due to the small amount of permutations, I'm seeing very similar results. Now I'm going to see, oh, calm down. There we go. Now we're seeing differing results where 0.056 is at the top. We're looking at this number right here, 0.075. So I might be able to, when I change it to 5,000 permutations for B, I get an interval. Oh, yeah. Just change your seed then. Put in a seed, Michaela. You are doing it correctly. You ran into the scenario where you increased the permutations and 0.05 is like my head, and 0.05 still stayed in the range. Guess what you have to do again. Please tell me if you think anything's weird on the grading on this, but technically, what do you have to do now? So since you increased permutations and 0.05 was still in the range, like methodologically, what should you do now? Like, because it's like a book question, because this is the great thing about statistics is there's randomness, so it's very hard to be like, this question is kind of set up in a way to make this usually follow a path, but you hit the path where you increased it to 5,000 and 0.05 was still in the range, so what would you do? Like in practice, if you see 0.05 is still in the range, you'd be like, well, now I need to do this again. What should you do since 0.05 is still in the range? Your interval's still inconclusive. Not increase the seed. That'll just change the randomness. So the seed, whatever the seed is, you could change the seed and you might, yeah. Like, at least like conceptual learning-wise, you could just change the seed, which might not be that bad theoretically to do. So you could change the seed. But technically what you should do, so now I'm going to increase the permutations. And so if 0.05 is still in the range right here, then what I'm probably, like the best sort of statistics, if 0.05 is still in the range, which is taking a while to run this, 0.05 is not in the range. But if 0.05 was still in the range, I should probably increase the permutations again. Does that make sense? It's going to make another tighter interval. So all we're doing is getting a more exact, precise estimate of what the p-value is. And you notice it's taking a lot more time to run this. But does that make sense, Michaela, that when you're doing this right here, you're going to get, and I have an idea. I'm going to take a quick look at this. I'm going to see if I can do it in, give myself 2 minutes to run this. Okay, so yeah, it's just a tighter interval. Your interval will get tighter and tighter and tighter. Is there some recommendations on what value we should use for seed permutation? Great question. So permutations, the more the better. So the more permutations you do, the better your estimates. It's a law of diminishing return. Really, I'm going to talk about this. I'm going to do it in a segment. So the question is, what's the best seed? What's the best permutation? So even though it asks for 5,000 question, yeah, just make sure I grade it right, because you could mention in your write-up, like, I still get an inconclusive interval. Right now, we would, increase the permutations more. So you can just put that in the write-up. I'm the one grading it, so if you don't think I graded properly, just be like, hey, Brian, in office hours, you told me to do this, and I did this, and you didn't give me points. Then I'll give you the points. So in technical sense, we would increase the permutations again. Do we need to add the plots for... You could turn off the plots for the second one. You can turn off the plots for the first one, too. You could do plots equals false. Yeah, I'm fine with that. Less output. You won't get points off for putting the output in, though. But you could throw in the arguments plot equals false. You guys are getting so good at this. Yeah, just thinking over those things like, do we really need the plots if we're not looking at them? You could just throw plot equals false. And that's just the argument we used today in class where we just did comma plot equals false, a new argument. Great job. Let's look at the question about what is the best seed, what's the best permutation. Good question right there. And here we go. So what is the best seed? What is the best permutation? Okay, so for best seed, there really is no best seed. Seed is just controls randomness. So use a consistent seed. Here's what you don't want to do. You don't want to start looking through seeds for the result you want, because you could just go through a bunch of seeds to find the one you want. It's like when you play Minecraft and you just find that world you want. And you're like, wow, I'm so good at Minecraft. I just load up 1,000 worlds and then find the world I want with all the resources, and I'm so good because I have everything I need. Are you really good at Minecraft then? Or are you just choosing a random seed that helps you out? So when you think about the right way to use seeds is maybe you have a seed you use. Like maybe someone's like, oh man, I'm all about that elite seed right there. Like, it's fine. If that's your seed, use that seed. But then don't be like, oh man, that didn't give me the results I want. I'm switching over to 320 seed. Don't be switching your seeds if it doesn't give you the results you want, because then you're redoing a randomness procedure and seeing what would happen. It's bad statistics. It's searching for results because you can get things by random chance. So you could use the seeds to your advantage to be like, oh, well, we ran it with this random seed and we got results. Well, did you run it with like 100 random seeds and you finally got results? Then that means, yeah. So don't do that. The proper way to use seeds is to use the same consistent seed. There is no best seed. Whatever seed you're using is just as good as another one. So whatever seed, doesn't matter. Now with permutations, more is always better. So you're like, man, I should just put in 10 billion permutations. Why would we not use 10 billion permutations? Just think theoretically, like, why is 10 billion permutations? And there's two issues with 10 billion. First one's rather obvious. So what is the first issue with using 10 billion permutations? I mean, computers are awesome these days, but there's a but right there. It's like, no, 10 billion permutations sounds great on paper until you try to run it. So one is going to take a long time to run this. Runtime, exactly. Runtime's going to take a lot of time. And then if you go back to some classical statistical equations, such as the confidence interval for the mean, which actually looks a lot like a confidence interval for like the slope. A lot of similarities between this equation right here. Let's say T star based on the percent confidence. And then we go here to the standard error. And the standard error will look specifically at this one. It's similar equations. I'm just going to write the standard error as S over square root of N. I want you to notice right here, this is important. Because of the way it's written, what you'll notice is there's a diminishing return. So this portion right here is your margin of error. And it's very similar down here when you do things like that's the standard error of the slope, which is the uncertainty in the slope, which is still based off of a sample size, and we would see diminishing return. So the second concept is not as obvious, but can be lightly explained mathematically. I'm not going into too much detail on it here, but think about this. If you go from a sample size of, let's say, 4 to 9, well, then you're dividing by, and I'm going to disappear right here, the numbers you would be dividing by for n would be, when you square root them, would be 2 to 3. If you go to 16, well, now you've gotten half, like you're dividing by 4. But when you get up here to a sample size of 100, well, then you're getting a tenth of what you want. And if you go to 400, well, then you have to get 4 times as much to get a 20 divide by. And just look at this increase right here. To get 1/2 of your return, because here's what you're dividing by when you square root it, you can go to 4 to 16, and you can have your margin of error, because this is all part of the margin of error. And if you get half down here, if you turn this into a smaller number, you'll get half the margin of error. So you get this diminishing return going from 4 to 9 to 16 to 10 to 100 to 400. And these are the numbers you'd be dividing by down here if this is your n. So these are all what n is equal to. N is equal to these, which then means you're dividing by these. So it's the law of diminishing return. So is running 10 billion permutations really necessary? your interval is going to be tighter, but I mean, after about maybe 1,000 or 5,000, it's diminishing return. You're going to see big jumps at the start. Your interval is going to go like, and it's not going to decrease as much. So does that make sense right there? Good questions on, so more permutations is always better, but diminishing return and time spent running permutations would limit us on like why we would do this. It's like, well, why not use 10 billion? I mean, yeah, if your computer can do it really quickly, maybe you work at Y12, sure, do 10 billion. Maybe you're working on my computer, maybe do a 10,000. Maybe you're working on a Chromebooks, do 500. Just differing computers, different processors, and different amount of return. So great questions. These are it's funny because that's such an important question. I'll hop back here to space. That question right there is the meat and potatoes. I want some meat and potatoes. Good filet mignon. Potato with some bacon on it. And some cheese, sour cream, chives. Oh man. Now I'm getting hungry. I haven't eaten lunch yet. We got a really nice restaurant here. I just want to go to it. Damn you, COVID. But that's the real question right here. Like, why not use more permutations? Why not do this? Those are the big questions. Let's throw some 20 points. I really appreciate that question because that's what we need to ask. Well, why don't we just do this? What's the best of this? Questions are what increase our knowledge. I try to remember that. You should always ask more questions than you try to answer. Because if you're answering a question, well, when you answer a question, especially if you're with someone you know, they can correct you if you're wrong. But if you just are always like giving answers, then you're never really listening to answers. So I try to remember this too, because I try to learn. I try. I fail. I want to examine number 5 here in a moment. I think I can examine it to see what % of the time. We can do it with a for loop. Let's see if you have a question, put it in the chat. I'm going to see if I can quickly examine number 5 to see what % of the time your results will come out. Let's take a look at it because I think I can examine it. It's part of the video we called like examining number 5. Let's take a look. Okay. So we've got here the code. Let's go grab the code. Let's go to this sheet right here. And let's put default permutations. Brian, can you help with 5B, specifically super practical statements? Yes. We'll take a look right here. So statistically, so let's talk about Trace's question first, right? And then we'll do our last part on this. Statistically, what do you notice here? We're comparing the means. Statistically, Michaela, just put it's inconclusive. You're fine. Just make sure to use a seed and everything, and then it'll replicate when you print it. Just tell me it's inconclusive, and I'll give you full credit. Just make, if I grade it wrong, just tell me. Be like, Brian, you said. I'll be like, is it? Fine. Don't worry. Funny, right? Because you don't know. The interval's just going to go like this, but it could still contain 0.05. That's the bad luck. And I want to answer the question about what % of the time would the interval come out inconclusive with random seeds. I want to see... yeah, don't worry about it. You're obviously understanding the concept, which is the whole point of this. The whole point is like conceptually to learn stuff. So one, is this statistically significant? I looked at the confidence interval and said, yes, it is since the p-value. Well, that means it's conclusive on statistical significance. So this is the conclusivity of the statistical significance. So it's conclusive that it is statistically significant because the p-value is below 0.05. So yes, statistically significant. And then it is conclusive on that. Now, this result right here, is this result statistically significant, yes or no? Just a quick yes or no on, is this statistically significant? I changed around the results right here. Is this result right here statistically significant, yes or no? So be careful, I'm trying to trick you. Is this result statistically significant? Ah, great job right there. Is this result statistically significant? I'm trying to trick you. Yes, yes, yes. It is statistically significant. It is. And why? P-value below 0.05. That's it. Just in your head. P-value below 0.05, statistically significant. Alpha, by default, is 0.05. P-value below 0.05, statistically significant. Boom, done. Now, what does this tell us down here, which goes back to the notes we were looking at just a moment ago? What does that... Oh my god, I'm hitting multiple musics. I'm not getting the permutation procedure up in my console. Might need to send me a screenshot of that. You should. Tell me, send me a screenshot on... I'm hearing noises. I should have my camera on in case I get like someone. I'll be like, hey, you. What does this tell us right here? Because we're getting an interval like this right here, which is not the same, but you can see this interval right here. And it's like, I don't know. I don't know. So when you look at this interval right here, what is it telling you? And it's a lot like this interval, which this interval is conclusive. This interval is what on the significance of this p-value? Like this is not significant, but this is conclusive because it doesn't contain 0.05. This is statistically significant, but this interval, because it contains 0.05, which it talks about right here, it's inconclusive. Not since the p-value is inside of it. Remember, the p-value will always be inside of it. It's inconclusive because why? Let me make sure this is highlighted right here. It's inconclusive. It's something like bootstrapping. Yes. Oh, you know some bootstrapping? Ooh, that's some good stuff right there. If you know some bootstrapping. It's something like we bootstrapping the p-value if we perform this test in some of the other simulations. That's pretty much what we're doing right here is we're kind of bootstrapping it. We're performing, it's almost like bootstrapping the p-value. Very, very close to that. Like conceptually, very, very close to make estimates of what the p-value would be because bootstrapping is a resampling procedure. So we're doing very similar to that. I should ask Peter to be like, technically, should we call this bootstrapped intervals? Because you know what? I think these might actually be, you know what? We're throwing 20 points because technically, because bootstrapping is a resampling procedure to see, you know, like what you use your original data set as the population and then create bootstrapped resamples of size of your population. And so, yeah, I think these might be bootstrapped intervals. I should check with Pete. I might actually look at it because I think these are bootstrapped intervals. Amazing. Like, yeah, it just doesn't say it. And I wish it said bootstrapped intervals. I'm pretty sure those are bootstrapped intervals. And you know what's interesting? They usually have a little bit of a right skew to them. If you looked at bootstrapped p-value intervals, they usually have a right skew to them. Amazing knowledge, amazing input right there. Thank you. The class is like, what the heck is bootstrapping? Resampling procedure. Don't worry. Don't worry. It's not on your test. But does this make sense right here, Trace? As we point out that 0.05 is in the interval, which gives inconclusivity to the bootstrapped p-value intervals right here. And I might look at the code here in just a second to double check. What's really great about the associate function is you got a lot of stuff going on in the background right here. For the associate function, you're looking at, you know, I think like 900 lines of code. And so what we could do is we can double check. And I think Trace, now the big question becomes, and so let's see right here. Here it is right here. Let's go right to the end of it. Binom test, more extreme, permutations, confident. So, okay, let me read on this screen. I sent my output to the console. Yes, let me take a look at that here in a second. With blank permutations, we're 95%. P-values in the range, we're 95% confident. Core extreme. Okay. Round C1. What is the object C1I? How C? Oh, it's in a list. CI is the taken from the binomial test. The more extremes vector from the amount of permutations. Confident taken out of that list of that object that creates that because there's a function creating it. Probably. Man, I'll have to look through this. This is good stuff right here. Really good questions. Let me look at what Trace has right here. And what did you say you were missing, Trace? Trace said they were missing. I'm not getting the permutation procedure output in my console. No, I think you're getting it. No, Trace, you have everything, right? What are you missing, Trace? You say you're not getting the permutation procedure output in your console. I might need to see, are you saying over here? Because it looks like, oh, you're not getting the top part. Are you not getting the top part of this, you're saying? Like, are you, because I don't think I saw this up here. That's weird if so. Let me take a look. Oh, you're right. It says permutation procedure, and then it's missing those parts. Can you send me your code? Send me your file. Let's take a look at that. Yeah, I just saw that right there. That's weird. You're not getting that part. So send me... Is it if you turn off the plots? Did you turn off the plots and then it doesn't give you that maybe? So maybe we don't want to do that. Okay, no, that doesn't do it. What is doing that? Why would it not do that? Good question right there. Just send me your code for this one if you want, like copy paste this code into there. And I'll take a look. I wonder what it is. I wonder why you wouldn't get that. And that's where the practical significance is going to come from. I don't want to quite say the answer to this one yet, but remember how we do it, you always want to give a number. See, Trace might message me downhill. Okay, do you mind if I pull this up, Trace? I think you're okay if I pull it up, right? So once again, the practical significance, since we're doing averages. Yep. And do you mind if I pull it up? Good to pull it up. Here, wait, I'll do put the screen. Yep, maybe that's how we do it right there, right? And then talk about it. Make sure to talk about this is the average number of people for parties based on whether people are smoking or not smoking. So I'm going to find that one part right here. I want to pull up like Pong or something. I don't know. I'm always afraid I'm going to like take something and someone will be like, you took my Pong GIF. I'm mad. Let's see right here. I'm looking at this one. Ooh, 5,000 permutations. Is that what it could be mad about? Okay, I think I got everything up and going. Ah! Can you send me which line of... wrong button. Can you send me which kind of line of code it is specifically? Because I'm getting it. I'm still getting... Maybe try knitting it. Is it okay if the knitted file shows the association tables and graphs? Mm-hmm. You can send it to me to double check, but you should be good. Don't worry if it's showing all this. That's perfectly fine. You just want to make sure you don't do things like print out like ex2 tips and print a whole data frame. Like that'll lose you points immediately. I'm not too like I'm pretty nice about not taking off points. People have lost points. Usually it's a second offense or it's a really bad offense. Like sometimes I'll put a reminder like don't put excessive output. Like you just want to think no one would ever look at this. Like if I print out a whole data frame right here to the screen, no one's ever going to look at this unless we're like, here's an appendix, I don't know what it's called, appendice, something like that, on the back of the report with the data frame so you can take a look at it. Which line of code is it? Yeah, email. I can always double check and be like, and that's always a great way to like double check right there. Maybe just reset R or try knitting it, Trace, because everything seems to be okay right here. I don't know why it would do that. And you can always, one thing I like to do is sometimes when I get a bunch of arguments is I always kind of like move it out like this, which you don't have to do. It just sometimes makes it easier on my eyes to see where everything's at. Y tilde x comma d equals seed equals permutations equals plots equal. Is it plots or plots? That could be part of the issue, Trace. That one says plot. You have plots right here, and so always check your autocomplete. It looks to be plot. Try changing plots to plot. I don't know if... Yeah, and try changing plots to plot. It might have done unused argument in those other ones. It was still running, which is interesting, but the argument looks to be plot and not plots. I probably said plots. And you can see right there, you can confirm. You got to watch out when it autocompletes. It'll throw in the extra equals. Restarting it, try knitting, try changing plots to plot. One of those should fix it because it's giving me the output. So it would seem more like the restart might fix it. Just sometimes we just throw things at the wall till something works. We're going to go back over here. I'm very interested in the question of how often would the question 5 give you an inconclusive interval? So we need to go right here. And then let's see if we can solve this. We're going to do a quick solve. Please ask questions if you have it. This is my question. Wrong button. So how often will question 5 give you an inconclusive interval? We have a version of question 5 right here. And what we want to do is we want to store the associate output. And can we extract what we need out of it? Oh my gosh, look at what X has in it. X has all this stuff. Warnings on... I don't know. What is going on right here? It's got shiny? Is this my actual X? This is so much stuff. I don't know if I can navigate through this. All I want's that interval. Oh my gosh. I don't know. All I wanted was that interval. To capture that interval. Someone help me. You know, we might have a problem, actually. The problem could be that it cats it to the screen. So since it... Because I think it's doing a cat right here, which just... What I mean by cat is the following. If I go like, hello... And that's not capturable. You'd be like, well, why don't you just save that into X, Brian? Well, when I save it into X, X is null. So just the little things... Awesome, yeah. Take a screenshot and then figure it out. Dude, perfect answer. Trace, great job right there. We're throwing some 20 points. So I think Dr. Petrie is using the cat. So we got to go back here to our favorite thing where we edit Dr. Petrie's function. So we're going to go and capture the output from Dr. Petrie's function to make our lives easier. And what we'll do right here is we will go and we'll look at the output for this function, ask questions if you have it. So we're going to use a little bit of coding right here to our advantage. So we want to get this interval, the p-value median test. Let's look for that in the code. There it is between CI1 and CI2. So actually what I'm going to do here is I'm going to do something really mean. What I'm going to do is I'm going to go right here. I'm going to go to return, and we're going to return the vector. You know what I'm going to do? I'm going to store this. No, we'll just return the vector. Return the vector CI1 and return the vector CI2 because I just want those values. So I've got Dr. Petrie's code right here. I'm going to call this Brian's function. It's my function now. And there it is. Brian's function is being stored. And we'll see if this runs properly. And we'll change this to Brian's function. And here we go. We're storing that. And it stored it. Cool. What was that? The medians test? Oh, we want the means test. Oh, no. We don't want the medians test. So let's go here. Whoops. Wrong test. And, oh, there it is right there. It's the same thing. Oh, good. And return, you'll learn this in 320 or 474. Return ends the function. So if I go right here and I do return right here, it'll end the function. So it doesn't matter that it's right there. And we're missing one parentheses on the return. So let's reevaluate our function. Now we'll capture the right interval right here. We're just returning at this point this interval. It seems that mine output on the p-value and practice parts inside the actual coding for some reason. But that's so... Oh, is it outputting it up in the window? Yeah, the different way you might have your R set up, it might be outputting it up here in the markdown file. So do this. Try running it over here in the console or try running it down here in the console. Oh, so great. Trace, 20 points. I think you figured it out, Trace. Just the way I have my R set up versus yours. Try doing it in the console. And so it looks to be capturing it maybe up here in the markdown file. So when you knit it, it will appear. But if you want to view it right now, unexpected. Okay, good. We're good. Yeah. So this should capture the output on this. And so now if you look at this, it captures the output with the interval. So let's go here and run this. And then we're going to take the code of the X, which is this. And so we'll see here. Let's go. Let's say X sub 1 or X value 1 is that good, is less than or equal to 0.05 is and 0.05 is less than or equal to, okay, so 0.05 is in the range for this. So what I'm going to do right here is I'm going to run 500 random seeds. So what have I just created right here? Trace, and then let's store this and say test value 1. And so Trace, what have I created what have I created right here? Any ideas what I just created and what I'm going to do with all this code right here to see what percent of the time, if we do this 500 times, so we're going to, we'll do it 200 times. So what have I created right here? We could create an estimate for the percent of time because we can actually use it with proportion test. What have I created right here, do you think? And what do you think the code's going to be? Because if you notice, I want to run this multiple times. So what I've actually created right here is a skeleton. My skeleton is going to use variable I. That'll go through 1 through 200. And we're going to go right here and just change the seed to I. And we'll just do 200 random seeds. Exactly. So we're going to reset this and we're going to run it. And now it's actually doing 200 random. Hopefully it goes quicker than that. There it goes. You see it's going. It's doing all these tests right here and finding out the intervals. And exactly. So, yep, great job right there. You can see it's just creating all these intervals, and then it's doing the test to see if 0.05 is contained in the interval, which you can see 0.05 is contained there. So it's going to track this for me, and then I can just do the mean of the vector to end it to find out what percent of the time 0.05 is contained in the interval. So you can see that one does not have it. That one does not. Ooh, got some ones that don't have it. Oh, wow, that one really didn't have it. And yeah, so we can go right here to the mean of the vector of x. And we can go here. We'll do one more thing after this. We'll write our remainder code. Prop test. Prop test, we need the amount, which will be the sum of x. And that'll be 200. And that should do it. So that should get us a confidence interval using these estimates right here. We have to wait for this. I could have probably just done it 100 times. 200, why not? How many times has it done it? Can we see our vector x while this is going away right here? Because if we can see the length of x, right? Oh my gosh, I'm a fool. Well, we're doing it 100 times now. I am a fool. No, I changed the plot window size. You know what we should do? That might speed it up a little bit. A little bit. Because I changed the plot window size and because this throws plots to the window, by changing the plots, it crashed the code because it tried to throw a plot to the window and it said, nope, plot too large for window, and it said, can't do it. And we should have an if in there. I think it should put a warning out and say, or a message, which if you've done coding before with functions and messages and warnings and all those different things, because that was an error that crashed the code. Not a warning or a message. There's errors, which will crash your code. There's warnings, which will just display red text, which still has your code continue. And then there's a message, which is just used for like, hey, you should know this. It's like different degrees when you have a message is like, hey, just in case you want to know. And a warning is like, hey, you should really pay attention to this. And error is like, no way, game over, stop, here's what you should know. And that's the difference between like a message, a warning, and an error. It's just differing degrees of how we're going to alert someone to something in our code. And you can see right there, some of the loops don't have 0.05. If you're wondering what I did, I went to Dr. Petrie's code and I made it so that his code would return, and return is what stops a function. So I went to where the means test was done and I put a return right here in the function. So I brought up his code, went to the part of the code I'm interested in, and that's why you see the code just stopping right here. It actually prints this out, and then it just completely stops because a return like stops the function. Let me take a look. Sure. Let me take a look there, Trace. Great questions. And we should be getting the end of the near of this for loop. It's taking, so it should take about 3-4 minutes because it's taking about 2-ish seconds each one. There's no practice between the average part size, only. Yeah, but think about this. Maybe it's a large scale restaurant, and like maybe since we see the non-smoking tables, is it? Yeah, there it is over there. You notice this doesn't change via random permutations. The non-smoking tables have a bit more people. It really depends on the context. Like if this is a little mom and pop shop, then you know, probably the small difference of a quarter of a person basically is not going to be that much importance to them. But if this is like large scale McDonald's, they might choose to go for more non-smoking, which is kind of a moot point. I don't think McDonald's has smoking sections. I think I remember that growing up. I mean, I remember smoking sections. Those went away in mid 2000s. But I swear I remember people smoking at McDonald's. Just like, walk up in line, someone's like, gotta finish my cigarette, and you're like, what's going on right here? What kind of world do we live in? Wait. No. Something's weird. Oh, it's the test vector. Ha ha. Ha ha. Mean of test. It's like, that's not right. Stop giving me graphic errors. Ooh. Yeah, let's do that next right here. We'll finish off with that. It actually looks like it. You know what's interesting? Oh, we didn't do 200 permutations. We only did 100. There we go. Yeah, there's a pretty good chance that your test will not be conclusive, which kind of worrisome to me. Somewhere between 52 to 71% of people, I'm 95% confidence, will receive a conclusive test. Or, no, this would be that's inconclusive. Yeah, somewhere between 52 to 71% of people should receive an inconclusive test. Our simulation right here showed 62% of the time the test was inconclusive. So we did a simulation right here by running random permutations. It's a book question. I like it. Now I'm liking it a little bit less because we show via random chance that 62% of the time you will get an inconclusive result, whereas the other, that doesn't mean you will get it 62% of the time, because somewhere between 52 to 71%, because there's uncertainty because we did a simulation. If you want to make it better, increase the simulation. So let's do that here in the background. While we talk about those book questions, we'll let this run, then we'll come back to this. We'll put this up to 400 permutations. And so let's go back here to the permutations. Or not the permutations, simulations. And I wish I could start it. You know what I can do to make life easier? There we go. That should do it. Now it's going to start at that, and it's going to append my vector. So here's another 300 random permutations being added on, and let's go take a look at those book questions and then come back to this and see if we get a better estimate, which is going to be a tighter interval. Right now our margin of error is about 10 plus or minus on 62%. More interval coming up soon. So we're going to take a look at those true-false questions right here. Let's go ahead and take a look at them, and we'll come back to see how the interval's doing in just a little bit. A little quick transition right there. So when we look at this right here, imagine the sample size is at least a dozen, which is not too tiny of a sample size. So a p-value right here is 0.003. The association must be statistically significant. How do you decide statistical significance? How do you decide statistical significance? So is 0.003 statistically significant? How do you decide statistical significance? When you look at this right here and you say, oh, the p-value is 0.003, must that be, yep, exactly right there. And when, use the default standard, because that's what everyone uses. I mean, you could say, well, what's alpha? It's like, well, what is usually alpha? Alpha is usually 0.05. And Trace, you got it exactly. It's less than 0.05. Boom. Now, when we get to the next one, the association must have practical significance. So with this, what C word we're talking about with practical significance right here? The practical significance is all the what of the data we're talking about. It's what all data needs. And to figure out practical significance, you don't look at p-value for, you need it to be statistically significant to be practically significant. More on that in a moment. Fisher woke up and decided that this level, it's good. You're talking about Ronald Fisher? Fisher's awesome. Some Ronald Fisher right there. Was he the one who was fighting with, no, that was it. Ronald Fisher was fighting with, Gossett, who created Gossett's teeth. I think it was Ronald Fisher. Fisher created the Fisher exact test. A lot of great stuff. Ronald Fisher right there. Really, really great statistician right there. Some class, a lot of stuff right there. Yeah, it's the context. And when we say it must have practical significance, it doesn't have to have practical significance. So does it have to have practical significance? I don't know. Let's look at the context. It could be practically significant because it is statistically significant, but it doesn't have to be. So the must right here is wrong. If we said this association could have practical significance, that is true. We can't say it must, but it could because it's statistically significant. This is the first question. This is the second. The association must be strong. I don't really care if you enter true or false right here. I've never really loved this book question because what do we mean by strong? I would say yes, it's strong enough that we were able to observe it, but strong as in a high correlation, you could say no. So frankly, I grade this one either way. I don't care. True or false, context, these are the ones that matter. I'm not saying what it is, listen to what I said. This one I don't care about that much. Let's look at the next one right here. A test for an association comes back with a p-value of 0.32. Yeah, exactly. Like, that's the biggest thing is like, what are we talking about here with vertical scatter? Oh, nice people. So the association must be statistically significant. So if we're saying that this must be statistically significant, or you could just say it is, this would be fine to say the association is statistically significant. True or false on this right here? True or false? The association is statistically significant. True or false? Yeah. Yeah, so thank you so much for saying this right here. Like as they're pointing out in the chat, you need to talk about if something is practically significant, and they're talking about clinical significance right there. Like maybe something's statistically significant, but then it's like, well, I mean, it's such a small difference that we don't care about it. Yeah, cool, we found out something, and this is definitely false. And then here's the thing, if something is not statistically significant, can it have practical significance? If something is not statistically significant, can it have practical significance? So if something is not statistically significant, we've already, this p-value here, right? Boom. It actually can't, because wait for it, my class knows what's coming. If it is not statistically significant, then the results we are seeing could just be likely due to what? And think about that. Just think about that. It could be due to random chance. So if it's not statistically significant, whatever we're observing, if there are differences, they could just be due to random chance. Like imagine I say, I have a friend who ate cheeseburgers the night before the test and they made a 90. I have a friend who ate a burrito the night before the test and they made a 70. Obviously, you want to eat cheeseburgers the night before the test. And you'd say, well, I'd be like, it's a difference of 20. That's 20 points difference on the test. My one friend ate a cheeseburger, made a 90. My other friend ate a quesadilla and made a 70, or I think a burrito. I can't remember. So there's a 20-point difference. First off, we don't have a large enough sample size for degrees of freedom if we're getting technical here. I'm waiting for them to jump in and be like, well, actually, can't run that test due to lack of degrees of freedom for the estimate of the variation between the groups. But let's say we could. We have two friends who ate cheeseburgers and we have two friends who ate burritos. Now we have large enough sample size to run the test. And the differences was 20 between the groups, but the p-value came back as 0.32. So even though the difference is 20, which is rather large, the differences could just be due to random chance. We don't have any real evidence that this difference of 20 is real. It could just be that we had two smart friends who ate cheeseburgers and two friends who are not as smart who ate burritos. And also, this is also not a controlled experiment. So we're not, randomly assigning groups, which gets into the medical stuff too, which when we hold variables constant, have random assignment, and have the element of control. So many great topics to go off from this, like to discuss further upon. But the big key thing for this one especially is statistical significance is the doorway to practical significance. So we start by saying, is it statistically significant? Yes. Okay, so now let's consider if we actually care about this. So the first question is it unlikely by random chance? Okay, yes. Now we get to talk about practical. So great question, great stuff. Let's throw some 20 points. I love talking about the medical stuff. I'm not big in that world, but I mean, I know some people who work in it. My brother works in it. Dr. Panel works in it. And so he'll talk a lot more about how like certain, we can't reject alternative hypothesis. Yeah, we only reject the null. We either reject the null or fail to reject the null. We have evidence for the alternative or we do not have evidence. So B3 is true since it says if it exists, the association must be weak if it exists at all. Yeah, it's kind of generally true. I don't love this third one that much either. I've talked to Petrie about them. Only the null, exactly. We only reject the null or fail to reject the null, which means if we reject the null, we're doing so because of evidence for the alternative. Exactly. And that's the language we use. The alternative is not what we reject or fail to reject. The alternative is what we will come to believe if we reject the null or not reject the null, which classic language is fail to reject the null. I like to say you reject or do not reject the null. And that means if you reject the null, you're doing so because you have evidence for the alternative. If you do not reject the null, you do not have evidence for the alternative, which is the same thing as failing to reject the null. My best way of describing this, which I do it in 201, is I say, I go to the mall. I don't go to the mall. Now, I don't go to the mall is the same thing as saying I failed to go to the mall. It's just the older way when people used to talk this way, like, I failed to reject the null. So it's either I reject the null or I do not reject the null, which is the same thing as I fail to reject the null. It's the same thing. It's just stats. People like to talk funny. Yeah, could you over question 3, part D? Let's do that here next. So you either reject the null or you do not reject the null, which is the same thing as saying I fail to reject the null. And when you reject the null, that implies, so we'll just do the classic language right here. When you reject the null, that means you have evidence for the alternative and not enough evidence for alt. I wanted it to be on the same line. No. There we go. So it's not, you just didn't have a sufficient evidence or not enough evidence. So when you fail to reject the null high p-value, there was insufficient evidence for the alternative. So if you have a low p-value, then there is evidence for the alternative because your results were unlikely, given that the null is true. Let's do the other question. Or you have p-hacked. Yes, classic p-hacking right there. Yep, just run a bunch of tests. And that's why we have the Bonferroni. You know your stuff. Don't p-hack. Bonferroni that if you're running multiple tests. Family-wise alpha. Here we'll put a little pause. But no, you are bringing up so many great points, and you know your stuff, because p-hacking is a major problem. John Oliver even mentioned it. Gosh, it's such an old thing. I wonder if I could find it because he's been on for so long now, but he mentioned p-hacking originally. It's when you run enough tests to basically, like classic p-hacking is running enough tests. And that's what we'd be doing by changing seeds. That's a little bit of p-hacking right there. If you change seeds to find the results you want, that'd be a form of p-hacking right there, which is hacking the p-value to find the results to be able to publish, because publish or perish. So you don't want to do that. If you're running multiple tests, you'll run a family-wise alpha, which can be done via Bonferroni correction. So you're hitting upon some really awesome problems and questions and things that we wrestle with. There's some Dr. Seaver for you right there. But those are the big questions. And keep asking those questions. Keep bringing these things up. These are things we need to think about. Question 3, pot D. Let's take a look at what that says. Management only cares about a difference of 1,000. Let's bring up those notes. Now, if management only cares about a difference of 1,000, or I'll put notes, so I got to make sure I'm on the screen while I talk about it. If management only cares about a difference of 1,000, that sounds like management is telling you that would be what significance to them. Management only cares about difference of 1,000. So that would be the what significance to management. Because this is always subjective and it's always the context. So if management says, we only care about a difference of 1,000 right here to maybe make decisions like, maybe we need to run promotions on a certain day, but we're really going to only focus on this whole promotion idea. Well, it's not that these intervals contain 1,000. It said, are the differences, that'd be the practical significance. Yep. So the management is saying, we want to know if there's more than a difference of 1,000 between days, because maybe there's something about, Saturday that makes it a higher day. We analyzed this way earlier. I'd have to go find the code I ran for it. We'll go look at we looked at the differences, and there was a difference of $333 right here. So to management, these differences are going to be rather what? Because they only care about a difference of 1,000, which I've kind of labeled my axis right here. So you can see 1,000 is about a length of that. And that's 333. We found it, check out the earlier part where we ran this a little bit, and we found that numerically is a difference of 333, which is the biggest difference, Monday to Saturday, and they're right next to each other, luckily. Other days are smaller in their differences. And we're not just comparing the days that are next to each other. It just so happens that the lowest median and the highest median are right next to each other. So this difference of 333 would be what to management? Because management only cares about a difference of 1,000. Management's like, hey, we don't want to meet unless you're finding differences of 1,000 right here in this data. So do you have a difference of 1,000? Is that what we're talking about when we see this right here? Yep, I maybe quote it. It's 300. If you want to quote it, you wouldn't know that without me telling you it or running code to find it, because this is the EX5 bikes data set. You wouldn't know that without me telling you, maybe. But visually speaking, you can tell that this is, you kind of have to squint if you don't have zooms like I do. But this right here is not nearly the difference they're looking for. So the management would say, whatever. That's what management says. I don't know. We're not doing anything with that. So yeah, maybe it's statistically significant, which is what we covered previously in this question, is there is statistical significance because your observed F statistic is up here. I'll just kind of plot that one out really briefly on here. Your F statistic is going to be right here. And that makes your p-value this, because the F statistic is 4.7, meaning that the variation between the groups was 4.7 times more than you would have expected, given that there is no association. The F statistic is a ratio. and we see a slightly large amount of observed variation. It's unlikely by random chance because there's very few permutations that would give results as extreme or more extreme than ours. And that's the p-value right there, and it looks to be close to 0. Definitely below 0.05, less than 5% of the random permutations would be more than this. Just visually speaking, imagine this is a bar of gold, and I say, here's your sliver. You'd say, Brian, you give me like nothing. Give me a little shaving off the bar of gold. And I'd say, yeah, I'm mean. So that's definitely less than 0.05. So it's definitely statistically significant. Certainty there, but management is telling us we don't care about it. Does that make sense right there, Trace? Good stuff. We'll hop back to space. Remember, you can always preload those questions. We're nearing the end, though. We're going to go look to see how our result did. We wrote a for loop earlier. Let's go take a look at that. So we wrote a for loop to see what error and prop test. What? How'd my code break? Sigh. What did I do to my code? NA. Oh, I think I know why. Well, I think I reset my test vector. So since I reset my test vector, let's go here to test 2 and take test elements 101 through 400. And let's just go here and run this with 300 I created. There we go. And last time we got a wider confidence interval, still around 62%. Last time it was 51 to 72 or 52 to 71, I believe. So we get a little bit of a tighter interval right here. Yeah. And we get about that return I was talking about. I was hoping to do the increase from 100 to 400, which was something we talked about previously about the diminishing return on confidence intervals. And this is not quite the confidence interval do. Could you go over 3B? It is another practical sequence, but I am struggling with giving a conclusive answer. Yeah, let's take a look at it. Let's hop back to space. That would actually be the p hat times q hat over n square root for confidence intervals for proportions, but similar idea. P hat times q hat over n square root confidence intervals for proportions. Is it the F statistic? Are you talking about the F stat one? Are you talking about the F statistic has been calculated for this data set and it turns out to be 4.7? What is the practical interpretation of this number? So is not practical significance. And here, I'll give some hints for this and definitely check out this video. So that's not the practical significance of it. It's kind of, it uses the word practical, but let's hop to the notes. So when we talk about the F statistic, oh, I don't have the full screen on. There we go. When we talk about the F statistic right here, we're talking about the observed variation between groups over what we would expect via random chance. And so I don't want to directly say the answer, but I want you to think about what we have right here. And this is kind of what we were alluding to during class. So definitely check out class's video from today. So I don't want to directly say it. But when we look at between group variation for means, and here's the between, like that is the practical significance right here. The two tests, test version A versus version B, had a difference of 8. And then what does the F ratio right here mean? Don't put it in the chat yet. And so the notes have some strong interpretations on this, talking about right here, and you do see some interpretations on the screen talking about what we see. So you kind of got some big hints right here on what the F is. Does this make sense, Trace? Like, I don't want to directly say it, and the ANOVA is going to test the variation between the groups when compared to means, and you can see as the F gets bigger, the p-value gets smaller, because that's, we see here 26.79 times 26.794 times more variation between the groups than we would have expected via random chance, given that there is no variation between the means, or no difference between the means, excuse me. So that was the graphic in red right here that I've marked with red. I observe 26.794 times more variation between the differences in means of the groups than I would have expected via random chance, given that there is no difference between the averages of the groups. Does that help out, Trace? I definitely take, you don't want to say quite that. That would be true anytime the F ratio is greater than 1, but focus in on kind of what these slides are saying, like what I'm saying and what these slides are saying. I'm thinking if another slide has it too. Like focus in on what I'm saying when I'm saying like, between the averages between the groups, we observed 26.7 times more variation between the means than we would have expected via random chance variation, given that there is no differences between the means. And focus in on kind of what these are saying. Like it is true anytime the F is greater than 1. Yeah, it is true anytime the F is greater than 1 that we observe more variation between the means than we would have expected. But the F being a ratio, and this is kind of one of the key words right here, tells you this, like the factor of how much more the variation is, because it's a ratio. So very important right there. The F is telling us like a factor increase of variation observed between the means than we would have expected due to random chance, given that there is no underlying variation, that they all have the fundamental same average. This is saying that there is no difference. They all have the same fundamental average. So that's like, I'm saying they all have the same average, and that's saying right there the fundamental assumption that there is no differences between the averages, which also in classical statistics would be that the null is true. One thing you'll notice right here is we often try to maybe talk about these things without saying the null, because a lot of people outside of stats world will not know what the null is. So if we say the null hypothesis, someone's like, the null? I think I learned that like when I was like 20. And you're like, oh, well, what we're assuming right here is that, if you take version A or version B, you would have the same average. And that's what the null hypothesis is if you take version A of the test or you take version B, you'd have the same average. But what we're seeing right here is that the variation between the means that we observe in our data is 4.7 times larger, hint, 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 than we would see given just random chance variation between the means if there was no difference between them. Like if test A and version B had the same fundamental average, then our differences we see right here are 4.7 times larger than we would expect given that assumption that they have no differences between their averages. And that's just better than saying, the null hypothesis states that true mean for A is equal to true mean for B, because classic stats, we always like to talk a little classic stats, is mu1 equals mu2. Or mu1 minus mu2 equals 0, and that's the null hypothesis, is that there is no fundamental difference. It's just no one's going to ever have you write out these equations. I mean, at least maybe for a technical paper or something like that, but in the business world, you're going to just be communicating these things to say, we're examining to see if there is a difference between the means right here, and we see that the variation between the means is 4.7 times more than we would have expected, given that there was no variation. So that's a pretty big difference, and practically significant right here is that the difference is 8 in test averages. So it looks to me that students would much rather take version B, and maybe we should see why their grades are so much lower or higher on each test. Great questions. Then between levels is close. Remember, throw in the last few parts. Let's go back to the notes real quick. Don't put the full thing in the chat though. I do not want to. Remember, kind of go off of this right here. Because you're kind of stopping right here. You're kind of you kind of stopped it right there. Maybe you have the rest. Don't worry. You could just don't. I think you're on the right track. You can double check with me via email. Whoops, I'm just gonna hit random buttons. But I think you're on the right track right now. And then you could say like between the days, because you're looking at between days, right? Yeah, because like the observed value of demand. But yeah, exactly, between the levels of days. I can't even read. Trace 20 points. Is that making more sense right there, that you're seeing a very large, like compared to what you would expect? Can we do assignment 3 question 4? Yeah, William, let's do it. Let's hop back here, please. Where's my music? Assignment 3 question 4. Which one's question 4? Is it? Wait. I think we just did it, William. Is it the true false? I think we just did it. What is the name for 10,000 points? It is the true false, William. So check it out. We just went over it for like 15 minutes. So check it out. I'll see if there's any last questions. Oh, no worries. I mean, if you jump in, I don't expect everyone to know. The name for 10,000 points, that level, is called... 10,000 is Brian tier. Is that what you're asking? There's 100,000, which is Galaxy Brian tier. They came up with these names. Any other last questions? Yeah, great job, Trace. Yeah, Trace, you're almost there at the 10,000 points. Nice job. Yeah, it's amazing to me looking at right now the students. It's good. There's just, you can tell some people are really watching a lot of class and some people are watching some class. 3,000 off Brian tier. Let's go. Yeah, you're getting there. You're actually 2,500 away, 2,500 something. I think you'll make it. I think you'll make it. It's tough. I want people to know. Just keep showing up, keep working. And it's... Oh, man. There we go. I'm just looking at the tiers. I'm looking who's at what now. Okay, I think that's got it. I'm going to go eat some lunch. Some good lunch. With that, any last questions? Thank you so much, William, and everyone, for understanding. I was like, we did a really good review of the True False. I think William's back in time watching True False right now. I'll mark this video later, so check it out. But for now, we're going to head off, go eat some lunch. Thank you so much, Trace. And excellent work. Keep asking those questions. Just keep thinking. I always want to kind of walk someone up to the answer and let them think about it. And you're doing an excellent job. Keep up the great work. We'll be back. I'm going to go eat some lunch. I'll talk to everyone later. Bye for now, everyone. Bye. Puppet Shark, where you at?